T5. Hello students, today we discuss a new chapter known as improper integration. In higher secondary, you have studied the proper integration. As for example, if we consider an integration 0 to 1 x dx, now this integration is proper in the sense that the range is finite. Lower limit 0, upper limit 1. And the function is itself bounded within the range of integration. And the first one, the range is finite and the function itself is bounded within the range of integration. 0 to 1 x dx. This is an example of proper integration. Now today we discuss an improper integration. If any one of the conditions is violated, then that integration known as the improper integration. Now I am presenting today's class. Hello, screen is visible. Hello.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
So I am starting the improper integration, or it is also called infinite integration. Normally it is improper integration. What do you mean by improper integration? We have already discussed. Now give an example. If we consider I a to b fx dx, then it will be improper. Actually, improper integration there are two kinds: first kind, second kind. First kind means range infinite, but function is bounded. E to the power minus x square dx 0 to infinity. Here the upper range is infinite. Second integration minus infinity to 1, the lower end minus infinity is unbounded.
Please zoom it a little bit.
Another zoom. Okay.
Yes, sir.
Last one minus infinity infinity, tan inverse x. This is the lower limit, upper limit, both infinite. So this type of integration is known as the improper integration of the first kind. Another integration in which range is finite, 0 to 1, second integration minus 1 to 2, range is finite, but the function is unbounded at any one point or more points within the range of integration. As for example, first integral 0 to 1 dx by x to the power 7, it is unbounded when x is equal to 0. And for second integration, it is unbounded at 2 points, 1 and 2. 1 intermediate point and 2 is the upper bound. So these two examples are the examples of improper integration of the second kind. So I hope you can understand what do you mean by first kind and second kind. First kind means range infinite. Second kind means range finite, but function is unbounded at any one, at least 1 point. Also there is a mixed kind, but normally we are generally mixed kind with 0 to infinity dx by x minus 1. Here range infinite, first kind, and also x is at x is equal to 1, 1 is the intermediate point, 0 to infinity. Function is unbounded. So this is an example of a mixed kind improper integration of mixed kind. Normally we are dealing with first and second kind. Convergence. Convergence means it takes the finite value. Finite value. Consider the integration at a first kind, a to infinity fx dx, which is an improper integration of the first kind. Now, if fx is bounded in a to capital X, where capital X greater than a, then first we find the integration a to x fx dx, and then taking the limit as x tends to infinity. So this is the procedure. Do not take the limit first chance. First you integrate the integrand within the range of integration a to capital X, and then taking the limit x tends to infinity, and test whether it is finite or not. If it is finite, then it is called convergent improper integration of the first kind, otherwise divergent. Similarly, second type, lower bound infinity, minus infinity to b. So
So
this
please
you
repeat
write,
that. I didn't understand.
actually a to infinity, first type is a to infinity. Now you do not find the value of the integration directly, but you change infinity by capital X, clear? And then taking the limit x tends to infinity. Clear?
Yes, sir.
Second, for minus infinity to b, then you write this in this way, x to b and x tends to minus infinity, and find whether the limit exists or not. If it exists and takes the finite value, then that integral is known as the convergent improper integration of the first kind. For this minus infinity to infinity, how to proceed? Minus infinity to infinity means minus infinity to a and a to infinity, where a is any point, or normally a is 0 or 1. So you proceed in this way for first kind. Minus infinity to infinity means minus infinity to a and a to infinity. Second kind, here range is finite, a to b, but function is unbounded. Suppose fx is unbounded at the end point a. We consider that the function is unbounded at the end point lower limit a, lower value. Then we proceed in this way, limit of a plus epsilon to b, where epsilon is a small positive number. So a plus epsilon is greater than a, clear? Epsilon small positive number, suppose 0.01. So a plus epsilon, which is greater than a. So first find the finding the integration, and then taking the limit a plus epsilon to b, and then finally taking the limit epsilon tends to 0 plus. And if it exists, then the integral converges, otherwise divergent. Clear? Similarly, if there is fx is unbounded at the upper limit b, then we proceed in this way. A to b minus a, b minus epsilon. Remember that b is the maximum point, so you always take b minus epsilon. But in the lower limit, you take a plus epsilon. Within the range, always consider within the range. And epsilon greater than 0, suppose 0.01. So b minus epsilon, which is less than b, so that it lies a to b. And then taking the limit epsilon to 0 plus, and so on. And finally, if c is a point lying between a to b, the function is unbounded, then proceed in this way. A to b fx dx, so limit of a to c minus epsilon plus c plus epsilon to b. Ekhane epsilon at epsilon dash, where a less than c minus epsilon, less than c plus epsilon dash, less than b. So this is the procedure taking the limit epsilon, and both epsilon and epsilon dash tends to 0 plus, and test whether it is exist or not. It sometimes happens that no definite limit exists when epsilon and epsilon dash tends to 0 independently, but that a limit exists when epsilon is equal to epsilon dash, and in that case we call the principal value, Cauchy principal value. That is, when epsilon is equal to epsilon dash, and the value of the limit on the right side when it exists is called the principal value or Cauchy principal value of the improper integration. And this is denoted by P. P means principal. A to B fx dx. The gallo mixed kind is not interested. Now you consider problem. So I hope theory portion you will clearly understand. convergence a to infinity dx by x to the power n. Now first take I is equal to this. As now dx by x to the power n is equal to x to the 1 minus n by 1 minus n, plain integration. Now consider different cases, n greater than 1. N is a power of x, n greater than 1. N greater than 1 and upper limit infinity. Okay. Then a to x dx by x to the power n is equal to limit of x tends to infinity this. Putting the value a to x, after integrating, putting the value, you will get this. And taking the limit, x tends to infinity. Had n is greater than 1, n greater than 1 and x tends to infinity. So, in the denominator, it is infinity. And 1 by infinity tends to 0. So, second part 0. And first part is finite. So, the integral converges for n greater than 1. As is convergent and the value is given by this. N less than 1. Then we proceed in this way. 1 minus n this. Now this is tends to infinity because here n is less than 1. So 1 minus n is greater than 0.
Sir, why is this convergent?
It's finite value, it takes the finite value. Clear?
I mean, sir, matlab,
n is finite, a is finite, small a given number.
yes, sir.
N is finite. So this is this takes the finite value and so it is convergent. But in the
Okay,
second case, here see that n is less than 1. So 1 minus n greater than 0. So if we take the limit x tends to infinity, then this is infinity minus something. So this tends to infinity. In this case, the I is divergent. Clear? So n less than 1 divergent, greater than 1 convergent. N is equal to 1. Taking the limit, this is log x. Again x tends to infinity, this is infinity. So I is divergent. Therefore, the above integral convergent for n greater than 1 and divergent for n is less than or equal to 1. So I hope the problem is clear. Very simple integration and taking the limit. Next, consider convergence of this type. This is the second type integration. This is first kind. A to infinity, upper limit infinity. This is first kind example. Second kind. Dx by x minus a to the power n. Here we see that at x is equal to a, the function is unbounded. Now we proceed in this way. Dx by this means this is integration, n not equal to 1. First case, 0 less than n less than 1. After integrating, you this value, and always you take epsilon tends to 0 plus and a plus epsilon. When lower limit unbounded, then you take a plus epsilon. But for upper limit, b minus epsilon. They are so very careful. After integrating this value, putting the limit a plus epsilon to b, this is the value. Taking the limit epsilon tends to 0 plus. Remember that n is less than 1. So 1 minus n is greater than 0. So if we take epsilon tends to 0, so this will be 0. So second term vanishes. First term is this, and this is finite. A, b finite, n is also finite. N lying between 0 to 1. A, b finite. So the integral takes the finite value, and that is why it is convergent. For n greater than 1. Again, taking the integration, considering integration, and then putting the value this. Here we see that n is greater than 1, so n minus 1 greater than 0. And taking epsilon tends to 0 plus, so it will be 1 by 0 plus, that is infinity. 1 by 0 plus means infinity. So this integral converges, takes the value infinity. So it is divergent. Therefore, we see that for n greater than 1 divergent and lying between 0 to 1 convergent. When n is equal to 1. Again log of x minus a, putting this, again infinity. Just putting the value, taking limit, so I is divergent. So the given integration convergent for n is less than 1, otherwise divergent. Another dx by b minus x to the power n, upper limit. Jokon function is unbounded at upper limit b. Proceeding in this way, same procedure. This is the integration. First take 0 to 1. Now this is equal to this, putting the range a and b minus epsilon. This is Remember that here you take b minus epsilon, not b plus epsilons, because b plus epsilon is greater than b. We always take find the value of the integration within the limit a to b. So we take b minus epsilon as a putting the value, and here we see that n less than 1, so 1 minus n greater than 0. So if we take epsilon tends to 0 plus, then second term vanishes, 0. And so this takes the value this, which is finite, and therefore I is convergent for 0 less than n less than 1. For n greater than 1, similarly procedure, epsilon tends to 0 plus, this is infinity. N minus 1 greater than 0, so this is 0 plus, 1 by 0 plus tends to infinity, and so divergent. N is equal to 1, definitely divergent. Now consider a theorem. If a function fx be positive in a to b, and a is only point of infinite discontinuity of fx in the same interval, then the necessary and sufficient condition of convergence or the improper integration this is that there exists a positive number mu independent of epsilon such that this is less than mu. A plus epsilon to b fx dx less than mu, where epsilon lying between 0 to b minus a. As a proof is beyond your syllabus. So this is the statement of the theorem. This is for second kind, a to b. The range is finite and only infinite discontinuity at the point a, lower limit. Second part, let fx and gx be two functions such that a less than x less than or equal to b, they are both positive, and fx is less than or equal to gx, and have point infinite discontinuity at x is equal to a. Then this converges if this converges. Since fx is less than or equal to gx, then if a to b gx just converges, then this one is less than, so it must be convergent. Convergent takes the finite value, so it is less than that value, so it is convergent. And this does not converge if does not. So you must commit to memory the statement only. A comparison test. Today we discuss only the comparison test only. Mu test in the next class. Let fx and gx be two functions such that a less than x less than equal to b. This is of second kind, both positive and have point of infinite discontinuity at x is equal to a, lower value. If limit of fx by gx x tends to a plus is equal to L, where L is any non-zero finite number, then the two integral this and this either both converge or both do not converge. One must be known, and if it is converges, then another one is also converges. So this is the theorem of the statement of theorem 9.3. Mu test next class. Now I consider another mu test for first kind. Let fx be positive, bounded and integrable in this. The necessary condition that a to infinity fx dx may converge is that a to x fx dx is less than m for s greater than or equal to m is a fixed number, finite number, positive number m. So we have discussed only the comparison test of the first and second kind. A to infinity fx dx converges if this convergent, and if fx dx are positive function this, and fx by gx extends to exist and is equal to a non-zero finite number, then this and this have the same nature, either both convergent or both do not converge. We do not interested today mu test. So next day I shall consider it. Now consider some problem. 0 infinity e to the minus s dx. This is the first kind. I is equal to this plane integration. বলো রেডি না? দাঁড়াও দু তিন মিনিটের মধ্যে ক্লাসটা শেষ করে দিই, তারপর করছি। হ্যাঁ ঠিক আছে, তুমি এটা পাঠিয়েছো? ওই লিঙ্কটা পাঠিয়ে দাও। আমি পাঠিয়ে দাও। আচ্ছা, 0 to infinity to the minus s dx plane integration. Putting this and taking the limit x to infinity. Remember that e to the power minus infinity is equal to 0. So value 1 is a finite number, so this is convergent. Very simple integration. Cos dx, sin t x by t, taking x tends to infinity. This limit does not exist. We know that the limit does not exist. So I does not exist. Minus e to infinity dx by 1 plus x square. Very simple integration, tan inverse x. But you proceed in the two kind, minus infinity to a to infinity. First kind, first type, minus x to a, integrating, taking the limit, and then finally x tends to infinity. Remember that tan inverse infinity means tan inverse infinity means tan inverse tan pi by 2. So it is pi by 2, finite number. For second part, it will be again pi by 2. So adding, you will get I1 plus I2. You will get this plus this is equal to pi. So pi is the value. This integral, so this integral converges and the value is pi. Actually, you have studied this type of integration in higher secondary, but remember that it is improper integration, not proper integration, since the range is infinite. Another problem, 0 to 1 dx by this. Very easy. Plain integration, putting the limit, epsilon tends to 0 plus. Here we see that lower bound function is unbounded. This is second kind, a lower bound unbounded. So plain integration, putting the epsilon tends to 0 plus, second term vanishes, so value is 3, finite number, so it is convergent. The value is 3. So today I do not proceed further because syllabus is not so lengthy.
Sir, can you please share the PDF?
Already shared.
Okay, thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
So you
Thank you,
must
sir.
study.
Thank you, sir.
Thank you, sir.
So this chapter is, I hope, very interesting.
Yes, sir. Very interesting.
Very interesting chapter. So you must
New type of
study
integration.
taking the printout, hard copy, and then read out. Then it will be easier for you.
Okay, sir.
So I am leaving now. Next class, I shall discuss the next part. Okay.
Okay, sir.